Alright, so this video will cover section 7.1 from our textbook for Math 1410 Linear Algebra for the spring 2017 semester. Section 7.1 is on an operation on matrices known as the transpose. The transpose is a fairly basic thing. It's simply the operation that interchanges rows and columns. So if I have an m by n matrix A, the transpose, written with the superscript t, is going to be, well, if I have m rows and n columns, and every row becomes a column and every column becomes a row, then I will have n rows and m columns after the transpose. Okay, so the rows of A transpose are the columns of A. You could equally well say that the columns of A transpose are the rows of A. And so one way to do this is to say that if A looks like, say, Aij m by n, and A transpose is some matrix with entries, let's say, Bij n by m, then Bij is equal to A j I. So switching rows and columns amounts to just switching the indices. Okay, so just for some quick examples, we'll do some more examples coming up, but just to get us started, let's say A looks like 2, 3, minus 1, 4, 0, 2. Okay, the transpose of A, the first row of A becomes the first column of A transpose, so 2, 3, minus 1. The second column of A becomes the second column of A transpose, 4, 0, 2. Right? And notice that I could have done it the other way. The first column of A becomes the first row of A transpose, the second column becomes the second row, the third column becomes the third row. Right? So you can talk about just interchanging the rows and the columns. Right? So or in terms of this sort of index notation here, we could say, for example, well, notice that the 1, 1 and the 2, 2 entries, those stay put, right? The 2, 2, 0, 2, 0, those guys stay, and everything else kind of pivots around there, right? So the 1, 2 entry becomes the 2, 1 entry. The 1, 3 entry becomes the 3, 1 entry, and so on. So that's really all that you need to know about the transpose. It's simply swapping rows and columns. It's quite simple. It's, you know, there's really nothing to it computationally. Certainly not compared to, let's say, computing an inverse. Right? Here are a few more examples. Okay, so for the first matrix, A transpose, so the first row becomes the first column, 2, 7, minus 8. The second row becomes the second column, 0, 2, 5. For the matrix B, again, rows become columns, 1, minus 1, 4, 2, 3, minus 1, and then 0, 4, 2. Again, notice that the diagonal is preserved, 1, 3, 2, 1, 3, 2, that stays the same, and then everything else kind of flips across, right? These guys get flipped, these guys get flipped, and these guys get flipped, right? So everything else kind of pivots across, you know, reflects across the diagonal, if you like. Okay, and finally the matrix C transpose, 0, 1, 2, minus 1, 0, minus 5, and 2, 5, 0. Okay, like so. Actually, let's let's say this is let's put a minus 2 in here. So if that was a minus 2 there, then this would become a minus 2 down here. With that modification, this becomes an example of what's known as an anti-symmetric matrix. Notice that this guy here is the negative of the matrix we started with. So C is an example of what's called an anti-symmetric matrix. So in a moment will define symmetric and antisymmetric matrices. Okay, and the symmetry here is the symmetry with respect to that diagonal, right? The idea that flipping across the diagonal should sort of, you know, preserve something. You should have some sort of mirror image, right, for symmetry. Anti-symmetry is you almost get the mirror image, but what you get is sort of the negative mirror image. Okay. All right. So that's the transpose. Here are some properties. We're not going to prove all of these. Most of them are fairly straightforward, right? The first one just says that if you take the transpose twice, you get back to where you started. That one's pretty clear. If I exchange rows and columns and then I change them back again, I'm back to where I started, right? The next one says that scalars can come out of the transpose again. That's clear. I mean, you can see it in our examples, right? If I were to multiply everything in, let's say, the matrix A, if I were to multiply everything in here by a scalar, right? Well, all the entries show up in the transpose, right? Every entry in A shows up in the transpose. They just show up in possibly a different spot. And so if everything was a multiple of some value k for A, the same is going to be true for the transpose, and you could pull that k out, right? So that one is fairly easy. The sum rule, right? That one also works out fairly simply, because if I you know, again, this is probably most easily understood in terms of the, you know, remember that we can kind of write things down in this index notation, and write that as aij plus bij. And swapping I and j, right, we can swap, so the transpose would mean swapping I and j here and here if we did the sum of the transposes on the left. Transpose of the sum would mean swapping I and j over on the right. Same idea, right? The fourth one, I'm not going to prove the fourth one. It takes a bit of work. You can do it. It's a bit of algebra. It's not that bad, but it's messy and it takes up a fair amount of room, so we're not going to do the proof. But you can think about it in the case, you know, if A is so let's say A is m by n and B is n by k. You can see why, if there is going to be a rule for the product, it has to be this one, because remember that in order to multiply A times B, right, these two values, they have to match, they have to be equal, okay? And the whole thing overall is an m by k matrix, right? And so if we transpose an m by k matrix, right, so A, B, transpose, we know that this should be k by m. And on the other hand, if we were doing, you know, if we do B transpose times A transpose, B transpose times A transpose, well, B, if I transpose B, I get something which is k by n. If I transpose A, I get something which is n by m. And notice that once again, those match up. And then I can multiply the two together. And I do get, indeed, something which is k by m. It is the right size. On the other hand, if I were trying to do A transpose times B transpose, right, this would be n by m, this would be k by n, and those don't necessarily even match, right? So the product of the transposes in the original order, that might not even be defined. Okay, so reversing the order, right, if there is going to be a rule, it's got to be this one, and we can work out the details if we want to. The fifth property, the transpose of the inverse is the inverse of the transpose. How do we see that? Well, if A is invertible, then A inverse exists, right? So if A inverse exists, that means that, well, I can take the transpose of every matrix, right? So this guy is defined. And also, if I do A transpose times A inverse transpose, remember, if I want to show that that this matrix here on the right, if I want to show that this guy is the inverse of that one, I need to show that when I multiply them together, I get the identity. So how do I see that? Well, I use the fourth property, right? I've got a product of two transposes. Reading the fourth property from right to left, this would be the same thing as doing A inverse times A, all transposed. But A inverse times A is the identity. And transposing the identity does nothing, right? The identity is just ones down the diagonal, zeros everywhere else, and the transpose leaves the diagonal alone. And so there we are. We've got the fifth property nailed down. Okay. Now, you may be wondering, I mean, sure, it's got some nice properties. You might reasonably wonder why we care about the transpose. What good is it for? And the short answer, I suppose, I mean, as far as this course is concerned, is that we can use the transpose to define symmetric and antisymmetric matrices. The longer answer about why we care about the transpose takes us into much, much more advanced linear algebra. We'd have to talk about dual spaces and duals to linear maps, and the transpose shows up in sort of this dual construction, which is something which you might see in 3410, but to be honest, it's probably even beyond 3410. So it's one of these things that it is important later on in linear algebra, and we show it to you now, so you've seen it before, but it's really hard to kind of get into the significance at this point in the course. Okay, so, but one thing we can do is we can define what it means for a matrix to be symmetric and what it means for a matrix to be antisymmetric. So a symmetric matrix is one that's equal to its own transpose. An antisymmetric matrix is like that one we saw earlier, where taking the transpose is the same thing as switching the signs of all the entries in your matrix. And symmetric and antisymmetric matrices show up in a lot of different places, actually, a lot of applications in chemistry and physics and other places, and a lot of places where you're applying matrix methods and linear algebra methods to the sciences. It's certainly not uncommon to encounter symmetric matrices, antisymmetric matrices. Okay, so here we have a theorem telling us that it's easy to construct examples of symmetric and antisymmetric matrices. Start with any square matrix A. If I take a matrix and I add it to its transpose, that's guaranteed to be symmetric. Why? Well, if I take A plus A transpose and I transpose it, well, if we look at our properties, okay, there's two properties. One is this one here, the sum rule. I can distribute the transpose over the sum. The other one is that taking the transpose twice gets me back to where I started. So using the sum rule, this is the same thing as A transpose plus A transpose transpose. And then I take the transpose twice on the second one, so I have A transpose plus A. And of course, order of addition doesn't matter, so this is A plus A transpose. And I'm back to where I started. Okay. If I had done A minus A transpose, well, then I get A transpose minus A transpose transpose, which is A transpose minus A, which is the negative of A minus A transpose. Okay, so we can establish that. The other result is similar. If I, let me just do it up here. I want a little bit of room at the bottom. If I took the transpose of A times A transpose, okay, then I have to use the product rule, which says I do the transpose of each one, but in reverse order. So transpose of A transpose times the transpose of A, and again, transpose twice gives me back A, and I'm back to where I started. Okay. Now, one thing that you might notice is the following. I could take my matrix A. If I take these two guys here, this one, and I add them together, what do I get? Well, the transposes cancel out, and I'm just left with 2 times A. So dividing things by 2, I can write A as 1/2 of A plus A transpose, and 1/2 of A minus A transpose. And because we also have this scalar rule, this guy here, okay, that tells me that, well, if A plus A transpose was symmetric, so would be 1/2 of A plus A transpose, and 1/2 of A minus A transpose will also be antisymmetric. And so what this tells me is that every matrix can be written as the sum of a symmetric matrix and an antisymmetric matrix. And this can occasionally be useful because there are certain properties that symmetric and antisymmetric matrices have that you might want to exploit. All right, that's it for the transpose. In the next video, we will talk about trace.